Let's talk about Huffman encoding. So I talked about this a little bit in lecture. Huffman encoding is compression, file compression. And it's a particular type of file compression involving different lengths of characters in files. When you normally have files, they have a fixed length encoding. Every character takes up 8 bits. This assignment, there's a lot of stuff about bits in the assignment. Now, you guys don't use bits very often in your computer science coding so far. You might think that you do. You might think about zeros and ones, or maybe we have problems with zeros and ones in them. But usually they're passed as ints and stuff, and so they're not truly bits. Like every char value in a C++ program is actually a byte, which is 8 bits. Every int is actually 32 bits, which is a whole 4 bytes worth of data. And so we don't think about the individual bits very often. It's possible to extract individual bits out of an int or a char using some certain operators in C++. But we just don't think about them very often. We don't have to. But anyway, the characters get stored as 8 individual bits. And I think you guys know binary, right? Like this is the 1s digit, this is the 2s, this is 4s, 8s, 16s, 32s, 64s, and 128s. And you sort of add up like 0 times 128. Plus 1 times 64, plus 1 times 32, no 16s, no 8s, no 4s, plus 1 times 2. So it's, whatever, 98 is the sum that you get. That's how characters are stored in the computer normally. That's called ASCII encoding, right? And every character has an encoding that's exactly 8 bits wide. Kevin, maybe you could email the coordinators, tell them I'll be 15 minutes. 8 bits wide. And that's fine. That's not so bad. So if you want to store a file that has 1 million characters in it, it takes about 1 million bytes, right? That's the idea, about a megabyte. But you could come up with some other encoding if you just dreamed up some other way of storing characters. And maybe you could come up with a way that would be shorter, that would take up less space. One way would be, instead of storing these with 8 bits each, store them with 4 or 3 or whatever. But I think what you have to understand is that there's only so much information you can pack into a given number of bits. If you only have 1 bit, you can only represent 2 things, right? 0 and 1. That's all it can store. You can't do more than that with 1 bit. If you have 2 bits, you can store 4 things, 0, 0, 0, 1, 1, 0, 1, 1. So, I mean, in general, it's 2 to the number of bits, right? 2 to the k if you have k bits. So if you have 8 bits, you can store 2 to the 8th unique values, which is 256. But nobody said every character had to be represented by the same number of bits. So the cute trick that you could do is, why don't you represent some characters using fewer bits and then some using more bits? You might say, well, how do I do that? Well, I guess the idea is, if you could represent all of them using fewer bits, we would do that, but we can't. But if we are able to make a trade-off of having frequently used characters use fewer bits and infrequently used characters use more bits, the overall result will be a smaller file, because we don't have very many of these, and we have a lot of these. And so really the question is, how do I come up with this mapping of a space is this and a z is that and all of this? How do I come up with this mapping? There's a formula. There's an algorithm for it. I'm basically making all of you guys use this, implement this algorithm for assignment 6. It's called the Huffman compression algorithm. It's a pretty famous classic compression algorithm. It actually, in real life, really is one of the major components of how zip works, like to compress files. It's not the only thing that's done by the zip program, but it's a big part of what zip does. So it has to do with binary trees. The whole point of the assignment is to practice binary trees. And I'm not going to spend very long on this slide, but basically there's an algorithm that will cause you to create a binary tree that will tell you these mappings. That binary tree would tell you to make a space be a 1, 0 and make a z be that long thing. That was what the binary tree would tell you. And the way the binary tree would tell you that would be, characters would be stored in the leaves of that tree, and the left versus right branches of the tree would tell you whether 0s and 1s should be used to make that character. So if you looked at this tree and went 0, 1, 0, that would be a letter C. So what that tree is telling me is that the encoding for the character C in this hypothetical example is 0, 1, 0. And the encoding for a B is 1, 0. And the encoding for an A is 1, 1, and so on. That's what that tree means. But of course, I haven't explained yet, how do I get this tree? Where does the tree come from? It's a step-by-step algorithm that takes sort of 4 or 5 steps to produce. The thing about this is, remember that the goal is for frequent characters to have short encodings and infrequent characters to have long encodings, right? And in order to do that, on this tree, what corresponds to that idea is the height of various leaf nodes. Like if you have to go down many hops to get to a leaf that has a character in it, that means that character has a lengthy encoding. So like, if we built this for a more sophisticated data set, probably the infrequent characters like z's and q's and stuff are down deeper, and the more frequently used characters are up higher in shorter branches. So that's kind of what shape that tree should have if we built that tree properly. Does that make sense? But how do you get this? How do you get this tree? So that's the next question. Well, there's a kind of a multiple step algorithm where you walk over the file and just count up how many times every character occurs. That'll tell you which characters are most frequently occurring. That's a good start, right? That'll tell you these characters probably should have short encodings and these other ones should have longer encodings. That's helpful. So once we've counted that up, there's a cute trick we can use with a priority queue that will turn those counts into that tree right there. And if we have that tree, we're in business, okay? So the counts are pretty easy. Wait, this slide is just a summary slide of the different steps. Count up the characters, use a priority queue, get the tree, walk the tree to get your character mapping. Let's walk through each step. That's more interesting, I think. So the first step, walk the file, count the characters, okay? And I made up this really short file for my examples, which, of course, it doesn't really indicate the benefit of the algorithm very well. But if you make up a longer file, it's hard to show all the data. So you say cab. In the actual original file, that's 9 bytes long. The A is a byte, the B is a byte. And I say byte, I mean 8 bits, right? 8 bits, 1 byte, same thing. So all these characters, including spaces, all that stuff is each 1 byte. We get to 9 bytes. You have cab. We think of the file as having this fake 10th byte at the end called the end of file byte. We give it a fake value of 256 because technically bytes can only be 0 through 255. So that's like an invalid value that we can pretend that it has, even though there's not really such a character in the file. But we add one fake character to the end, which helps our algorithm function properly. I'll show you why in a second. But we add that there. Now we have this 10 bytes, and we loop over those bytes, and we just use a map. We just map from what character we see to how many times we've seen it. We've done counting examples like that plenty of times before. If you just loop over the characters and count them up in this map, you end up with this set of counts, right? It's 2 spaces in there. There's 3 A's, there's 3 B's, there's a C, and we have one fake EOF, end of file character, right? Okay, you count those up. That's not that hard. That doesn't even use the new material for this week, but now what you do is you make a priority queue. I think this is the first part of the algorithm that people find a little bit confusing, so we'll walk through it, take questions if you guys are stuck on this part. You make a priority queue, and you put all the counts out of the map in here. You make little structures or nodes or whatever, objects. These are basically, I think of these as tree nodes, but we'll talk about that in a second. You put in character information into a priority queue, and the ordering of the priority queue, the priorities come from frequencies, from counts, basically. So the priority queue, things come out with the smaller priorities up to the higher priorities, right? That you guys just implemented that, so you know that. And characters that have small count are earlier toward the front of the queue, I guess, conceptually. They're going to come out faster if you say DQ, right? And characters that occur lots of times are going to be later in the PQ, and they're going to come out later, right? So you pack these in, but I guess what's important to understand is you have to remember not only that this character is in here, but kind of like a little node of information about it, the count and the letter, both, as like that's the element of the priority queue. Okay? And we actually call these little things with a count and a character, we call that a Huffman node. So you kind of make a priority queue full of Huffman nodes with those information in them. Now, we use this funny algorithm over that priority queue where we repeatedly pull out 2 nodes from it. And since it's a priority queue, that's going to mean pull out the 2 nodes that have the smallest count of occurrences, right? Pull them out, and then put them back together as a binary tree, and then put the binary tree back into the priority queue. Let me show you. The pictures make it easier. You start with this. You DQ those 2 nodes. Those are the ones with the lowest frequency, so they come out first. You make a new node, a new tree node that has these as its left and right children, and you put that parent back into the priority queue. So the EOF and the C come out, and what goes back in is a new node with them as its children. And the key thing is the node that has the C and the EOF as its children, it's got a counter of frequency of occurrences of its own, and that's the sum of everything underneath it. So if it has left child has 1 occurrence and the right child has 1 occurrence, then that parent, its count is 2 total occurrences. And you put that back in the heap in the priority queue. And the key thing about that is that 2 sorts itself in with all the other ones because it's supposed to be like in order with priority with all the other ones, right? So the new thing you add back in sorts itself into the proper place in the heap according to its priority relative to the other ones, right? So this is the state after one iteration of this algorithm, of this loop. Now we do it again. We pull out the front two, which are the space and the daddy node of the other two that we had here. Those come out. We put a new parent on them. And again, that parent has the sum of its children. So it now has a priority of 4, right? So when we put it back in, we put it back in with a priority of 4. And the only other things in the PQ are going to be these guys with 3s on them. And so actually the new thing with the priority 4 is higher priority than them. So what comes out after we do this step is this. We've got the 2 3s and this whole mess here, which has a priority 4 at the top of it. So it's slid over to there. We just keep doing this. We pull these two out, put a parent on them. The parent has a priority of 6. We put them back in. And the thing with the 6 is, now this is these two. The priority queue is these two here, these two things. And they're in this order because it's 4 and 6. And now we just keep doing this algorithm until there's only one element left in the priority queue, which represents basically everybody. We pull the 4 and 6 out. We slap a parent on them. That's our tree. That's the tree we wanted in the picture a couple of slides ago. This thing, this tree, tells you binary representations, bit representations of all these characters. Because you can pretend that going left means a 0 and going right means a 1. So if I want a space, I go left, left, and I get a space. That's a 0, 0 for a space. If I want a C, I go left, right, left. That's a 0, 1, 0 to get a C. And so this goofy algorithm produced this thing that can produce those character mappings that can produce smaller files and compress files for me. Okay? So that's one of the biggest parts of the algorithm. It's one of the trickier parts of the homework assignment is getting that to work. And this slide here just illustrates that 0, 1, left, right kind of aspect that I was talking about. If I gave you this tree, like if I gave you a pointer to the root of this tree, could you write a function that would walk the tree and emit all of the character mappings, emit that a C is a 0, 0 or 0, 1, whatever? Like, could you output that to me? That's basically what I'm asking you to do in this assignment. You could do it recursively, right? You could walk around in the tree, you could traverse the tree, and when you got to leaf nodes, when you got to these things, you could somehow keep track of how you got there, what decisions you made on the way. Oh, I went left twice to get to here, therefore 0, 0 is my printout, that kind of stuff, right? That's what you're doing here. Basically, after you had this tree, if you walked all around the tree and gathered up, okay, a space is a 0, 0, and an A is a 1, 1, and so on. If you wrapped all that up and put that into a map from character to binary encoding, that map would look like this. An A is a 1, 1, a space is a 0, 0, and that's what those mappings would be. Once we had that map, we wouldn't really need the binary tree anymore, right? The mapping now just, if you want to compress a file now, you can use this map, loop over the original file, and as you see the characters, look up what their encodings are and output the encoded version instead of the original version, right? I see an A, okay, that's a 1, 1. I see a space, oh, that's a 0, 0. And so you're just outputting those bits. You're outputting a compressed version of the file. And so if you really did that, you see an A is a 1, 1, and a B is a 1, 0, and a space is an 0, 0. So I'm just looking up all the characters in here and putting the equivalent mapping. And when we're all done, if you count up all the bits that takes, it takes a total of, I don't know, what is it, 22 bits to encode that. The one special thing we do is we have to put in an end-of-file character at the end of there so that we know when the compressed bits are done. After all that, there's 22 bits. On the computer hard drive, a file must take up a full byte. You can't stop in the middle of a byte. So even though we had a couple of bits left over, they're still there, they're zeros. But like that is 3 bytes of data to represent ab, cab. And originally, I believe it was like 9 or 10 bytes. So we went from that down to 3. We compressed it by about a 1/3, down to 1/3 of its original size. So that's kind of what we got out of that here. Yeah?
The overall that you're writing there, how does the code now when a letter like A or B ends?
Oh, how does it know when the letter ends? You're asking about
like 1, 1, 1, 0. Like if this is a longer encoding, like 1, 1, 1, 0 could be like Z or something, and then.
Right. So like, how does it know? Like, I compressed this. That's great. You're actually asking about decompression, right? Like, yeah. I put this out into the file. This is my compressed file. And then later, if I want to get this back, how do I know what these bits mean? As you say, like maybe there's a Z that's 1, 1, 1. How do I know it's not a Z? How do I know it's an A, B? Yeah, exactly. I think it's a really great question, but the cool answer is that it just works. And I'll show you, it works out. This won't be a problem. But before I show you that, though, I want to make sure, like, do you guys have questions so far about, like, how I get to here? I mean, you know, when you go do it, it's harder to do it than to draw it. But, I mean, do you sort of understand conceptually sort of so far where we're at? Yeah. Everyone's either nodding or sobbing quietly. I'll assume you're doing OK. OK, so then, I mean, how do we go the opposite direction? How do we decode? Well, there's a really cool property that naturally comes out from this algorithm, which is what I'll call the prefix property, which means that no character's encoding is entirely a prefix of another character's encoding. Let me define that. Let me be specific what I mean by that. Like if A has the encoding 110, then that means there will not be any other character whose encoding starts with 110. There might be characters that start with 10 or 011, but not 110 as the start. It might be a substring, it might be the ending, but never the start of any other character. So what that means, that nice property, just you'll have to trust me that that is the property that comes out from this algorithm. I guess if you don't trust me, let me give you another proof of it. If another character started with the, like if the where is it? Here. If space is 00, I'm promising no other character starts with 00. You know that's true because that character would have to be under this for that to be the case, right? And nothing's under these leaves. These leaves are leaves. So no character other than space begins with 00. OK, because that's true, you can simply do this greedily. When you're decoding later, if you see 00, you just say, oh, that's a space. You grab those and you treat them as a space, and you immediately move on. You never keep going. If you match, you just keep reading bits until it matches something, and aha, that's what character that is. And then you go on, and it works. It just works out. So to decode, you just read one at a time from the input. Actually, it's best if you have the tree. You just read a bit at a time. And if you read a 0, you go left in the tree. If you read a 1, you go right in the tree. And you just keep doing that until you get down to a leaf. And boom, that's the character that should come out, the decompressed character that should come out. And once the character comes out, you need to go back up to the top of the tree and start over, because there's probably more bits to represent the next character. So you just go up, walk down, oh, it's an X. Go up, walk down, oh, it's a space. Go up, walk down, it's a Z. You just do that until the file comes out, the original contents of the file. That's how you decompress. You use the same Huffman tree that you built in the compression step to do the decompression. So that's kind of the idea of the assignment. Like here's an example just to really hammer this home in terms of decompression. Like if I gave you this input and I said decompress it using this tree, you'd say, well, OK, I see a 1, so that means I'm up here, I go right. I see a 0, that means I go left. Aha, so that's a B. So you just right away, you know. And then go back to the start, you know, erase, right? And then 1, 1, okay, 1, 1, that's an A. I mean, you see what I'm doing here? And then, OK, go back to the start. And then I see 0, 1, 0. That's a C, so that's a C. And you know what I mean? You just keep doing this, and eventually I think you get to the point where you see a 0, 1, 1, and that tells you that's the end of the file. Then you immediately stop. And you got to stop right away when you find that, because there might be some stray zeros. I think I showed you sometimes you have a half of a byte at the end of the file, and you just want to stop because there might be some stray zeros there, and those zeros might be thought of as spaces or characters if you aren't careful or something. So the moment you see the end of the file, the pseudo, the fake end of the file character that we added earlier, that's where your algorithm sees that and it stops going. So that's the decompression step. Now, there are a few details here. I mean, the concepts are one thing, and hopefully we're getting some clarity on the concepts. But the implementation details in terms of what you guys have to do, I'll pop up in a second kind of some of that. Like, you basically have to write functions that correspond to these different steps of this algorithm that I showed you. And hopefully there will be a natural transfer from the pictures to the functions. But in terms of like bits, you have to write some code that reads and writes bits. And you can't really do that using if streams. I mean, when you do a read on an if stream, you guys have written things like, you know, get line or just the arrows or that kind of thing. And those read entire lines, entire strings at a time. You can even use a function called get or read that reads you a single character at a time. But even that's too many, because that's like 8 bits. I just want a bit. And there's no function on an if stream to read a bit. And so we provide special classes for you in this assignment called I bit stream and O bit stream, input bit stream and output bit stream that do have methods called read bit and write bit, which, I mean, if you're curious, basically we wrote them, we read a whole byte and remember it, and then for the next 8 calls we return its bits, and then when the 9th call we read the next byte. We'll just save that from you so you don't have to write that part. But these are things we provide for you on the assignment. You could read and write an individual bit at a time. One thing that's funny is you pass the bit as an int. So like it's just funny because you pass in 4 bytes and 31 of them of the bits are useless, basically. You know, you only use the 0 or the 1. But anyway, that's how you read and write a bit. Now, in terms of the assignment, the last thing I'll maybe pop up before we just talk and have questions and stuff is just if you look at the spec of the assignment for the Huffman encoding, here, you have to write a file called encoding.cpp. And the functions that you write correspond to the steps of the algorithm that we talked about. So like step 1 is count the frequencies of the characters, like we said. Step 2 is build the binary tree by putting them in the priority queue. That's step 2, right? Make this tree. This looks familiar, doesn't it? Step 3 is build the map by walking this tree and saying, oh, the 0, 0 means whatever, means a space, right? Step 4 is actually use this to spit out the compressed data. So, I mean, you have to write functions called build frequency table, which means like count the characters. That's step 1. Build binary tree. That's step 2. I'll give you the frequency table from step 1. Like basically each of these functions, what it returns is the parameter for the next function. Like this one returns this, and that gets sent into here for this. This one returns the root of the binary tree. The root of the binary tree is passed in over here to create the encoding map, which says like this character turns into 0, 1, and this character turns into 1, 1, 0, and all that kind of stuff. That map gets passed in as the parameter to the 4th step, which is to actually encode the data. So now I really will give you the file and say, here, using the map that you built all that time with your binary tree and your priority queue and all that stuff, here, now compress this file. Open it up, read each character, look it up in the map, and write out the compressed version of it out to the output, the O-bit stream. So read the input file, use these mappings to dump out a compressed version of it to there, to that output bit stream, write the bits out. And then decode data is just decompress it. So I'll give you the bit stream of input, and here's the root of the binary tree with the 0 and 1 stuff in it. And I want you to write out the decompressed version to that output file. And that's basically what you're doing. There's 2 more methods, one called compress and one called decompress. And those methods like basically wrap all the steps up so that the user wouldn't have to call step 1, step 2, step 3. Just do all the steps. Here's the input file name, here's the output file name, do them all. And you just call your own functions in sequence to achieve that. That's basically what we're up to on this. Did you want to add something? Yeah.
Yes, and if you want more detail, there will be more hours on Monday.
There's another session? Awesome. So Rishi's going to really do one on Monday. Yeah, he'll probably, I would still recommend potentially going to that one because he'll probably have some insights that I didn't give today. Do you want to add anything while we're here, Kevin?
The one tricky thing that it's mentioned in the handout and in bold on the handout, but still causes a lot of problems. If you notice, you have to read your file twice, right? Once when you actually build your encoding tree, and then once to actually use that tree to encode your data. And if you need to rewind your file between the two, otherwise, you're trying to read the file again, but you've already read it, so it's already gone.
So you're talking about this compression function. Yes. The compression function means just do everything. Like, here's the input file, here's the output file. Run all your little step 1, step 2, step 3, all those functions I was talking about just a minute ago. Run them all so that the end result is that output file has the compressed output. And you're right. What Kevin said is you have to read over the whole file in the very first step just to count the characters up, right? This occurs 3 times and that occurs 12 times and so on. But by doing that, you walk the input stream to the end of the file now. And then in the later steps of the algorithm, you want to walk through the file again using your binary tree and your map and stuff so that you can actually dump out the compressed contents as you see them. But in order to do that, you have to rewind the stream back to the beginning, and then you'll read it. But that's a pretty common bug students have. But I think the SLs in the layer are just trained to, they're like, oh, you have that bug, put rewind. So that's a pretty common one that students run into.
Rewind, put basically the input stream again on the top?
Exactly.
Yeah, there's a... Yeah, there is a, what does it say? See the input-output streams section? What does that mean? rewind.
There's a method that's actually called rewind stream.
Yeah, there it is.
So.
You just say rewind stream. I mean, it's just a one-line call, but not having that line means when you try to read the file again later, it looks like it's empty. And a lot of students are like, my compression doesn't do anything. So that's because you already ate up all the file to count the characters, and now you're at the end. So yeah, anyway, there's obviously more details than this, but that's kind of the overview. Did anybody have any more questions? Yeah, go ahead.
I don't know if I can word this properly. When you're building the tree, you have the 1 and the 0 decision. Are at the byte level, is 1 and 0 similar in terms of memory usage?
So the question was, are zeros and ones kind of the same? Does it matter? Does one use more than the other? They're all the same. You're not trying to minimize ones. Zeros and ones each are just bits. So really, I mean, honestly, you could take the entire tree and reverse it, and the algorithm would be equal in its effectiveness. But you would have to be consistent. The way that you compressed it, you'd have to decompress it to match that, or else your file would be gibberish on the other side, right? So if you bent your tree backwards, they'd have to match. But there's no benefit to having more ones or more zeros. Really, all that matters is how many bits you end up with. And it's kind of fun. Once you get this working, you can actually run it. You can compress any kind of files. All the examples I did today are text, like abs and cabs and stuff. But this really will work on like images and MP3s. And it's kind of fun to like run it on files and see. You might find some files compress better than others. And it's interesting to think about why. We can talk about that later sometime. But try it out once you get some of it working. And of course, there's a demo solution you can run where you can try and see. One of the things you'll find about the main, like we wrote the kind of main runner for this one. And it has options in the main menu to let you test each individual piece. And of course, what you want to do is write one and get it totally working and test the hell out of it, and then go on to the next one, right? Because everything builds on the previous steps. But the nice thing about it is that the main menu that we have really lets you dump out like all the stuff in your tree, all the stuff in your maps. And so hopefully, if it isn't right, you can really track down and see a good printout of kind of what's going on and what help you find what's wrong if you need to.